Model performance analysis of XGBoost for predicting stock prices. Investors and traders can greatly benefit from accurate price predictions in the stock market, which is a complex and dynamic environment. Machine learning algorithms, such as XGBoost, have gained popularity in recent years for their ability to analyze and predict stock prices. XGBoost is applied in this analysis to predict stock prices, evaluate the model's performance, and visualize the predictions. The dataset begins with historical price and volume data for a particular stock. In order to prepare the dataset for training and evaluation, the code performs various pre-processing steps, including data manipulation and feature engineering. In order to capture relevant patterns and trends in the data, moving averages, MACD, and RSI are calculated. The dataset is then divided into training, validation, and test sets. While the training set is used to train the XGBoost regressor model, the validation set is used to select the best hyperparameters. Afterward, the trained model is evaluated on the test set. In addition to the analysis, visualizations are provided to provide insights into the dataset and the model's performance. The model's predictions and their alignment with actual stock prices are displayed in charts displaying actual and predicted stock prices as well as various technical indicators. A feature importance plot reveals the importance of different factors in the model's decision-making process. Various data analysis and visualization tasks are performed by this Python script. The program imports several libraries and sets up the necessary configurations. The code starts by importing several libraries, such as OS for operating system functions, NumPy for numerical calculations, Pandas for data manipulation, XGBoost for gradient boosting, and matplotlib.pyplot for plotting. Next, it imports specific functions and modules from the XGBoost library, such as plot_importance and plot_tree, which visualize feature importance and decision trees, respectively. Also, it imports modules related to data preprocessing and model evaluation from the sklearn, scikit-learn library. A number of these modules are included in the package, including mean_squared_error for calculating mean squared error, min-max scaler for scaling numerical data, train_test_split for splitting data into training and testing sets, and grid search for tuning hyperparameters. Using pip, it installs the package decompose to perform time series decomposition. A time series can be broken down into its trend, seasonality, and residual components using this package. Afterwards, the code imports modules related to chart drawing and visualization from the Plotly library. It includes Plotly as Py, Plotly.io as PO, Plotly.graph_objects as Go, and various other modules for rendering charts offline and online. The next step is to suppress warnings from the sklearn library using the simplifilter function. Future and deprecation warnings are hidden in this way. Plotly can display charts in notebook mode when running in a notebook environment. As a final step, it sets up a default layout, defining the background color and other visual properties for all visualizations created with Plotly. The program creates a figure object with the specified layout and assigns it to the fig variable. In addition, it sets the layout template as the default template for all Plotly visualizations. Read historical prices for the stock I am analyzing, for example CERN. Over the past 10 years, the New York Stock Exchange dataset provides daily price history. To reduce the amount of data to be processed, I cropped the time frame and started from 2010. To keep the data frame clean, rows are removed and reindexed. The purpose of this code snippet is to load and prepare a specific dataset related to the stock market. It defines two variables, ETF_name and ETF_directory. This value represents the name of the ETF, exchange-traded fund, being analyzed, which in this case is CERN. The ETF_directory specifies the location of the dataset files. After reading the ETF data from a CSV file, the code uses the Pandas library's read_CSV function. This file path is constructed by joining the ETF_directory, the lowercase version of the ETF_name, and the extension .as.text. For cross-platform compatibility, this is done with os.path.join. Data is loaded into a Pandas data frame called df. The code then manipulates the data frame with some data manipulation steps. This function converts the date column to datetime format using the pd.to_datetime function. Afterwards, the data frame is filtered to keep only rows with a date column greater than or equal to 2010. A subset of this data is assigned back to the df variable. After filtering, the code sets df.index equals range len df to a new range of indices. As a result, the index values are consecutive integers starting at 0. Lastly, the code displays the first few rows of the modified data frame using df.head. To verify that the ETF dataset has been successfully loaded and preprocessed, this preview is provided. OHLC chart. To get a sense of historical prices, I draw an OHLC chart, open/high/low/close. I have drawn a volume chart below OHLC, which shows the number of stocks traded each day. I explain the importance of OHLC and volume charts in my previous notebook, linked above. To visualize stock market data, this code snippet uses the Plotly library. In order to create a plot, it first initializes a figure object called fig using the make_subplots function. A 2-row, 1-column layout indicates that the chart will have 2 subplots stacked vertically. The code then adds a trace to the first subplot using fig.add_trace. A OHLC chart is created by passing the necessary data to the go.olk function. For the x-axis, the data frame's date column is used, and for the y-axis, the data frame's columns for open, high, low, and close prices are used. df.open, df.high, df.low, df.close. Price is the name given to the trace. The row and col arguments specify that this trace should appear in the first row and column of the figure. Using fig.add_trace, the code adds a second trace to the second subplot. It creates a scatter plot by passing the date column as the x-axis data and the volume column, df.volume, as the y-axis data. Volume is the name given to this trace. The row and col arguments indicate that this trace should appear in the figure's second row and first column. The code updates the layout of the figure after adding the traces with fig.update. As a result, the design change modifies the layout _axis_range slider _visible property to false, which hides the range slider for zooming in on a specific time period on the x-axis. Finally, the code displays the figure using fig.show, displaying the OHLC plot in the top subplot and the volume scatter plot in the bottom subplot. Users can analyze price trends and trading volumes using this visual representation of stock market data. The decomposition process. Using the STL decompose package, we can decompose a stock's closing price into its trend, seasonality, and residual components, and visualize the results. In the first step, a new data frame is created by selecting only the date and close columns from data frame DF. Using double square brackets, the subset is created, date, close. This method ensures that the new data frame is a separate copy of the selected columns. A data frame is created by setting the date column as the index using the set_index method. Based on dates, this allows for easier manipulation and indexing. A check of the changes is made by displaying the first few rows of df_close data frame using df_close.head. An example of a modified data frame with the date column set as the index is shown here. The next step is to decompose the closing prices using the decompose function from the decompose package. The decompose function takes a data frame as input and specifies a period of 365, indicating that the decomposition should consider yearly seasonality. The function separates closing prices into their trend, seasonality, and residual components. As a result of decomposing the data, a figure object named fig is created using the plot method of the decomp object. A plot of the decomposed components is generated. Finally, the size of the fig object is set to 20 inches in width and 8 inches in height using the set_size_inches method. When displaying the decomposition plot, this adjusts the figure's dimensions for optimal visibility and clarity. Indicators of technical strength. Moving averages. The following moving averages are calculated to be used as features: $SMA_5, $SMA_10, $SMA_15, $SMA_30, and $EMA_9. This code snippet calculates and visualizes various moving averages for stock closing prices. To begin, the code calculates the exponential moving average, EMA, using the EM function applied to the close column of the data frame DF. Averages are calculated using the mean function, and values are shifted by a position using shift. The calculated EMA values are stored in a new column called EMA_9. A simple moving average, SMA, is then calculated using the rolling function applied to the close column of the data frame. Using the rolling function, You can compute the average over a specified window. SMAs are calculated with window sizes of 5, 10, 15, and 30 periods. To calculate the average, we use the mean function, and to shift the values, we use shift. New columns called SMA_5, SMA_10, SMA_15, and SMA_30 are created in the data frame. The moving averages are calculated and a new go.figure object called fig is created. Using fig.add_trace, the code adds multiple traces to the figure. The traces represent different moving averages and original closing prices. On each trace, the date column is used as the x-axis data, and the corresponding moving average column or the close column is used as the y-axis data. To identify the moving average represented by each trace, it is given a name. As a final step, the figure is displayed using fig.show. The chart shows the moving averages, EMA, SMA5, SMA10, SMA15, SMA30, and the original closing prices. To make the close trace less prominent, the opacity is reduced to 0.2. Technical analysis of a stock's price movements can be enhanced by analyzing the trend and crossover points of its moving averages. Index of relative strength. The RSI indicator will be added to predict whether a stock is overbought or oversold. A stock's relative strength index, RSI, is calculated and visualized in this code snippet. We define a function named relative_strength_x which takes a data frame df and an optional parameter n, by default 14. RSI values are calculated based on stock closing prices. Inside the function, the closing prices are extracted from the data frame df and assigned to the close variable. Using the diff function, the price differences between consecutive days are calculated, and the result is stored in the delta variable. Since the first element of delta is nan, it is excluded. In order to separate positive and negative price changes, two copies of delta are created, prices up and prices down. Prices up retains only positive values from delta and zeroes out negative ones. In the same way, prices down keeps only negative values from delta and sets positive values to 0. With the rolling mean function, the code takes the rolling mean of all prices up and down over n periods. It calculates the average gains, roll up, and average losses, roll down. The relative strength, RS, is computed by dividing roll up by the absolute value of roll down. The RSI values are then calculated using the formula RSI equals 100, 1 plus RS. RSI values are assigned to a new column called RSI in the df data frame by calling the relative_strength_x function with df as the argument. RSI columns with missing values, nan, are filled with 0. As soon as the RSI is calculated, a go.figure object called fig is created. Using fig.add_trace, the code adds a single trace to the figure. This trace uses the date column from the df data frame as the x-axis data and the RSI column as the y-axis data. RSI is the name given to the trace. To display the figure, fig.show is used, displaying a line chart representing the RSI values over time. Using this visualization, we can analyze the stock's momentum and potential overbought or oversold conditions. The MACD is hash. In this code snippet, we calculate and visualize the moving average convergence divergence, MACD, indicator. Using the closing prices of the stock, two exponential moving averages, EMAs, are calculated. EM is used with the span parameter set to 12 and 26, respectively. The EMAs are assigned to the EMA_12 and EMA_26 variables as pandas series. Next, the MACD line is calculated by subtracting the EMA_26 values from the EMA_12 values. This difference is assigned to a column called MACD in the df data frame. Based on the MACD values, another exponential moving average is calculated to generate the signal line. This function is called with a span parameter set to 9, indicating the number of periods to consider. A new column in the data frame called MACD_signal is created to store the resulting values. Utilizing our make_subplots function, a new figure object is created after calculating the MACD and signal line. 2 rows and 1 column are used to set up the layout of the figure. It is possible to add multiple traces to the figure by using the function fig.add_trace. 3 traces are added to the first row and first column, 1 for the closing prices, close, 1 for the 12-period EMA, EMA12, and 1 for the 26-period EMA, EMA26. These traces represent the stock's price and the two EMAs. In the second row and first column, two traces are added, one for the MACD line, MACD, and one for the signal line, signal line. The MACD indicator and the signal line are represented by these traces. The figure is displayed using fig.show. The chart shows the stock's closing prices, the two EMAs, the MACD line, and the signal line. Analyzing the MACD indicator's trend, crossovers, and potential buy or sell signals is made easier with this visualization. Adjusting the label column, the close price column is shifted by -1 rows to forecast the next day's price. With this shift, the features for day $D_I$ align with the corresponding timestamp, such as $RSI_I$, while the price Canadian $I plus $1 corresponds to the next day. A data frame's close column is shifted using this code snippet. To move the values in the close column by one position, the code uses the shift function. The parameter -1 indicates that the values should be shifted one row upwards. Shifting the values in the close column results in each value being replaced with the value from the next row. By doing so, the close prices are aligned with the subsequent time frame. This code prepares the dataset for predicting future values based on the features of the current row. Changing the close column to the next day's closing price allows models to be trained to predict future prices based on the available features at a given time. Hash drop invalid samples. If moving averages are calculated and label columns are shifted, a few rows will have invalid values, i.e. $SMA_$10 has not been calculated for the first 10 days, for example. In addition, the last row price is equal to 0 after shifting the close price column. It should be helpful to remove these samples. This code snippet focuses on manipulating the data frame DF by modifying its rows and index. The first line of code, df equals df.illic33, selects a subset of rows from the data frame starting from index position 33 and assigns it back to the df variable. The purpose of this operation is to remove any rows that were affected by the calculation of moving averages and MACD lines, as those calculations may need some initial rows of data in order to be accurate. The second line of code, df equals df-1, selects all rows from the data frame except for the last row and reassigns it to the df variable. The previous code snippet shifted the close column upward, making the last row's close price irrelevant for prediction. Excluding the last row aligns the dataset with the shifted close prices. In the last step, the code sets the index of the data frame to a new range of values by using df.index equals range_len df. Using this method, the data frame is re-indexed with consecutive integer values starting at 0. Upon removing rows and resetting the index, this step ensures that the index values reflect the new subset of data. Stock data frame is split into three subsets: training, $70/%, validation, $15/%, and test, $15/%. The split indices were calculated and three separate frames were created: train_df, valid_df, test_df. The chart below plots all three frames. With this code snippet, you can split a data frame into training, validation, and test sets based on specified proportions. Initially, the code defines the proportions for the test set, test_size, and validation set, valid_size. The proportions indicate the size of the test and validation sets relative to the entire dataset. According to the proportions, it calculates the indices at which to split the data. The data frame's rows are multiplied by the proportions and converted to integers as a result. Data is divided into training, validation, and test sets using these indices. Next, three new data frame variables are created: train_df, valid_df, and test_df. As the training set, the data frame contains rows from the start of the data frame up to the valid_split_ix index. This table contains rows, starting at valid_split_ix plus 1 and continuing until the test validation sets, which is the validation set. The test-defined function includes rows from test_split_ix plus 1 to the end of the data frame, representing the portion reserved for the test set. In order to create the figure object, log.figure is used after splitting the data into two. Using fig.add_trace, three traces are added to the figure. A trace represents one of the three data splits: training, validation, and testing. X-axis data is from the date column of each data frame, and Y-axis data is from the close column. To identify the data split each trace represents, training, validation, test, it is given a name, training, validation, test. The last step in the figure is to display a line graph showing the close prices for all three sets of training, validation, and test data. Data splits can be visualized and understood using this visualization. Columns that are unnecessary should be dropped. In this code snippet, specific columns are dropped from the training, validation, and test data frames. Firstly, a list is defined called drop_calls which contains the names of the columns to be dropped from data frames. The columns specified for dropping are date, volume, open, low, high, and open end. The code then removes columns from each data frame. For the train_df data frame, the drop function is used to remove the columns specified in drop_calls by passing 1 as the second argument. Columns are being dropped as a result of this. Reassign the modified data frame back to train_df. In the same way, the valid_df and test_df data frames undergo the same process. Data frames modified by drop_calls are reassigned to valid_df and test_df, respectively, after the columns specified in drop_calls are dropped. This code removes the specified columns, date, volume, open, low, high, open-end, from the training, validation, and test data frames. By selectively removing unwanted columns, it is possible to concentrate on the relevant features that are needed for training and evaluating predictive models. This prevents unwanted columns from influencing the analysis or adding unnecessary noise. Labels and features separated. For training, validation, and test datasets, this code snippet creates the target variable and the feature variables. This code creates a new variable y_train by copying the close column from the train_df data frame. The target variable is the variable we want to predict or forecast in this column. In the next step, the code creates the training set's feature variables. A new variable called x_train is created for the remaining columns of the train data file, excluding the close column. The feature variables represent the independent variables used to predict the target variable. Furthermore, the code creates variables y_valid and y_test by copying the close column from valid_df and test_df data frames. Validation and test sets are stored in these variables. Following that, the code creates the feature variables for the validation and test sets. In addition to the close column of valid_df and test_df, the remaining columns are assigned to variables x_valid and x_test, respectively. Finally, the code calls the info method on the x_train data frame, which provides information about the structure and type of training features. In this step, we identify the characteristics and properties of the training dataset, including the number of columns, data types, and any missing or null values. The XGBoost regressor needs to be fine-tuned. The code snippet demonstrates how to perform a grid search to find the best hyperparameters for a gradient boosting model, specifically an XGBoost regression model. In this code, %time measures the execution time by using magic commands. To tune hyperparameters, a dictionary called parameters is defined, which contains different values. Among the hyperparameters are n_estimators, learning_rate, max_depth, gamma, and random_state. A grid of parameter combinations is created by specifying multiple values for each hyperparameter. For both the training and validation sets, an evaluation set is created that contains tuples containing feature and target variables. To monitor the model's performance during training, this evaluation set is used. This model is instantiated with the XGB.XG regressor class, and the evaluation set is passed to the model using the eval_set parameter. To perform regression with mean squared error as the loss function, the objective is set to reg squared error. To suppress unnecessary output during training, the verbose parameter is set to false. A grid search object called CLF is created to contain the XGBoost regressor model and parameter grid. A grid search is performed by evaluating all combinations of the specified hyperparameters and selecting the best set of hyperparameters based on the validation score. As arguments, we pass the training features, x_train, and target variables, y_train, to the fit method on the CLF object. Hyperparameters are selected by training the model using all possible parameter combinations. It then prints both the best parameters found, clf.best_params_, and the corresponding best validation score, CLF.best_score_. Based on these values, one can identify the optimal hyperparameters and the performance of the model. Using the best hyperparameters from the previous grid search, this code snippet trains an XGBoost regressor model. The %time magic command measures the execution time. XGBoost regressors are instantiated using the XGB.SG regressor class. The best hyperparameters found from the grid search are passed to the model using the CLF.best_params_ syntax, which allows you to unpack the dictionary of best hyperparameters as a keyword argument. To perform regression with mean squared error as the loss function, the objective is set to reg squared error. In this method, the training feature variables, x_train, and target variables, y_train, are passed as arguments. A training evaluation set is also included to monitor the model's performance. To suppress unnecessary output during training, the verbose parameter is set to false. A XGBoost regressor model is trained using the best hyperparameters obtained from the grid search by executing this code. To minimize the mean squared error loss, the model learns from the training data to make predictions on unseen data. This training process is measured using the %time command. In this code snippet, we generate a feature importance plot for the trained XGBoost regressor model. The plot_importance function is called, passing the trained model as the argument. A built-in feature of the XGBoost library, this function visualizes the importance of different features in the model's predictions. The code generates a plot showing the importance of each feature in the trained model. A plot shows which features have the greatest impact on the model's predictions. In general, features with higher importance values are considered more influential in determining the target variable, while features with lower importance values have less influence. The visualization aids in understanding the relative importance of different features and in identifying areas for further research. Predictions can be calculated and visualized. By using the trained XGBoost regressor model, this code snippet makes predictions and prints the predicted values alongside the actual values for the target variable. In this implementation, x_test_ variables represent the feature variables of the test set that were passed to the predicted model. Based on the provided test data, this function predicts the values of the target variables using the trained model. The predicted values are stored in the variable y_pred. The code then prints the actual values, y_true, for the target variable by converting the first 5 elements of y_test to a numpy array using np.array and displaying them using the print function. A similar pattern is followed in printing the predicted values, y_pred, by displaying the first 5 elements of the y_pred array. This code displays the actual value of the target variable as well as the predicted value. By comparing the actual and predicted values, the trained model's performance and accuracy can be assessed. In this code snippet, the mean squared error, MSE, between actual values, y_test, and predicted values, y_pred, for the target variable is calculated and printed. Using the actual values, y_test, and predicted values, y_pred, as arguments, the mean_squared_error function is called. In the scikit-learn library, this function computes the mean squared error, a metric commonly used to evaluate regression models. Using the print function, an informative message is displayed along with the mean squared error value. By using the f-string formatting, the mean squared error value is embedded in the printed message. This code displays the mean squared error between the actual and predicted values for the target variable. As a measure of how well the model's predictions match the actual data, the mean squared error is calculated. A lower mean squared error indicates that the model's predictions are closer to the true values, whereas a higher mean squared error indicates a larger discrepancy. In this code snippet, we visualize the predicted and actual prices for the target variable. A data frame called predicted_prices is created by copying the subset of rows from df starting from the index test_split_igs+1 until the end. The test set is represented by this subset. Rather than modifying the original data frame, the copy function creates a new one. Next, the close column in the predicted_prices data frame is updated with the predicted values, y_pred, replacing the original values with the model's predictions. A new figure object called fig is created using the make_subplots function. 2 rows and 1 column are created by this function. The function fig.add_trace adds multiple traces to the figure. The first row and first column contain 2 traces, one for the actual prices from the original data frame, df.close, and one for the predicted prices from the predicted_prices data frame. As part of the chart, both traces have been assigned names, truth and prediction, respectively, and marker colors. A second row and first column are added, with two traces, one for the actual prices, y_test, and one for the predicted prices, y_pred. However, these traces are not given legends, show legend equals false, to avoid redundancy with the legends in the first row. After that, the figure is displayed using the fig.show function. There are two rows in this visualization. The first row presents the actual and predicted prices for the entire dataset, while the second row zooms in on the test set to provide a closer look at the predicted and actual prices. A visual comparison of the predicted and actual prices allows an assessment of the model's performance and accuracy. In this analysis, XGBoost has demonstrated promising results in predicting stock prices. Stock prices were accurately predicted with the help of gradient boosting and the XGBoost algorithm. Metrics such as mean squared error, MSE, were used to assess the model's performance. Generally, the lower the MSE value, the more accurate the model's predictions are. Visualizations, including line charts and feature importance plots, offer valuable insights into predicted and actual stock prices. By analyzing the model's performance, they can reveal trends, patterns, and areas for improvement. The inherent volatility and unpredictability of the market make stock price prediction a challenging task. While XGBoost has shown promising results, it is always advisable to consider other fundamental and technical analysis techniques when making investment decisions. Finally, this analysis highlights XGBoost's potential as a powerful financial tool in predicting stock prices. Ultimately, the results provide a basis for further research and improvements in stock price prediction models, enabling investors and traders to make well-informed decisions in the volatile stock market.